Okay, our next speaker is Stuart Mills from Star Dundee. I think you get the award for greatest distance to the workshop. Perhaps. They come from Scotland.
Okay, as you heard, I'm Stuart Mills. I'm lead software engineer at Star Dundee. And for those who haven't heard of Star Dundee, we are specialists in spacewire technology and related fields, so we're heavily involved in research. We're a spin-out from the University of Dundee, so we have a strong relationship with the University of Dundee. And this is a research project I'm going to speak about. So we took the approach of implementing a new protocol on a new processor on RTEMS, which was an operating system we weren't familiar with. Might have been stretching it a bit far to try all those new things, but so far it seems to be going quite well. So the work, most of the protocol work was done by Dave Gibson at University of Dundee. We have a small problem in Dundee that there's lots of people called Dave. So we have Dave Patterson from Star Dundee, who has done most of the software development related to supporting RTEMS, debug environments and testing. Steve Parks, our managing director, has been working on the standard that I'm going to speak about, and I have the pleasure of presenting this to you. Most of my involvement has been at the management level, so I can't take any of the, well, I can take the flak for it going wrong, mainly. When I asked the three guys to give me some slides, they each gave me about 30, so I had to cut this down a little. I'll try to zip through it as quickly as I can. I'm going to introduce this new processor that Atmel are developing, our support for RTEMS on that platform, both porting to RTEMS and also a debug and test environment that we needed. I'll briefly go over Spacewire-D, the new protocol, and then I'll speak about the implementation on the Castor processor. As I'm going to zip through this quite fast, if anyone's got any questions, just put your hand up. I'll try to look. So the Castor processor being developed by Atmel, it's a complete system on chip for spaceflight. If you were here last year, Steve Parks presented in great detail, so I'm not going to go into it too much. There are Spacewire protocol engines which were developed by Star Dundee. There's also Mill Standard 1553, CAN. It's low power, high performance, radiation tolerant. If I give you a look at the architecture diagram, that'll give you a better idea. There's the three Spacewire engines, a Spacewire router. It's a Spark V8 processor with lots of access to internal and external memory. The Spacewire engines offload all Spacewire communications from the processor, so it's entirely independent. There's support for the remote memory access protocol, both an initiator and target. The target can be directly to memory, so there's no involvement at all with the processor, or you can use software to authenticate. The initiator, you can queue up commands to be initiated, and that's all handled separately from the processor. There's a protocol multiplexer and demultiplexer which can route to each of the DMA channels or to the RMAP target and or initiator. And then there's a router as well, and we have a timecode controller. So that can be a timecode master, or it could be used to send individual timecodes or Spacewire broadcasts, interrupt codes, which is a new development in Spacewire. There's comprehensive debug support on board, so you can set breakpoints, single stepping. That's all accessible via JTAG, Spacewire, or UART. We have a prototype board. This is running at 40 megahertz. Final board will run at 200. Lots of memory, the Spacewire engines, router, timecode controller. And we have just the Spacewire and UART for debug at the moment on board. This is a compact PCI card. So we wanted to support RTEMS on this board. First thing, we need to be able to debug and test. There's no point in writing software if we can't debug. We have a software development environment which is based on Eclipse, which is available for some of the existing Atmel processors. We sell a Spacewire RTC development environment and test board. So we already had that available. It supports viewing the internal registers, the trace buffer, and so on. So we ported that to work with Caster. That involved adding support for the changes to the register map and other bit field assignments for the new registers and so on. And we needed GCC support, so we needed device-specific libraries and linker scripts. I've got a few examples of some of the views here. This is the Leon 2 FT registers. This is one of the memory configs. You can see that you can view each of the individual bits within the register, and these are broken down so you can actually see what values each of the fields has. This is some of the Spacewire peripherals. This is one port 3 control and status, so you can see whether the link's running, whether there's been any errors on that link. Then there's a trace buffer and the Leon cache. So we had a test environment, a debug environment. Now we needed to port RTEMS to Caster. I think this is probably taken straight from one of Dr. Joel's slides, how to create a BSP for RTEMS. So we looked at whether there was an existing board, a BSP for an existing or similar board, and whether the board CPU was supported. Then we looked at board initialization and the important drivers. The Caster port was based on the existing Leon 2 BSPs with clock and console drivers. We then added Spacewire DMA channel driver, RMAP target and initiator driver. We will add other device drivers in future, but that's enough for the purposes of this research. In parallel with this, we also ported RTEMS to the RTC chip, which was also used in this investigation. The performance, as I said, we're running on a 40 megahertz clock at the moment, but this is the expected performance for a 200 megahertz clock. We expect it to be very low latency. With the Spacewire engines being independent from the processor, we expect to be able to reach the maximum theoretical rate on the 200 megabits per second links. And the 3 engines will all operate in parallel autonomously. So, Spacewire-D is something that has been discussed for a number of years. Spacewire typically used for onboard data handling, not for control applications. Spacewire doesn't offer determinism out of the box. A single Spacewire link's deterministic. If you send a packet, you'll receive a packet over that link within a bounded time period, unless something goes wrong, obviously. A larger network, though, as soon as you start introducing routers, there's the possibility of blocking, and there's no guarantees that a packet will reach its destination within a certain time period. So a way of introducing deterministic delivery is to use time division multiplexing. So Spacewire has the concept of time codes, which can be used to indicate various events. Normally they're sent periodically, so you can use a Spacewire time code sent periodically to indicate a time slot. So the time slot, there's 64 possible time slots from 64 Spacewire time codes, and each time slot has the same number as the time code. So here we go, time code 6 is received, so we're currently in time slot 6. Time code 7, we're in time slot 8, and you won't be surprised to find out time code 8, time slot 8. So this can be used to break up the network access into slots. In Spacewire-D, we're looking at time slots in the range of 1 to 15 milliseconds, which gives an epoch or epoch of 64 time slots of around 0.1 to 1 second. The example here for a 200 megabits per second network allows reading between 20 and 300 kilobytes per time slot. That assumes that the time slot is kept, the traffic is kept transmitting and receiving throughout the time slot. There will be acknowledgements, so it depends on how you configure your transactions as to whether that's possible. But this is sufficiently timely for avionics applications, we believe. Schedules are used to arrange, to avoid conflicting use of the network. In a single slot, you might go for the simple option of having a single initiator, which can speak to one or multiple targets. That means there's going to be no chance of contention on the network during that time slot. Or you might have multiple initiators which are working independently and not speaking to the same target, not using the same routers, or not using the same links in the same direction. They can actually access the same routers. This is a design decision, really. Spacewire-D offers 4 services. The first of these is static bus, is the only deterministic one. The reason that there are other services are, although there's deterministic and not deterministic, there are often classes of determinism, even though these dynamic and asynchronous buses would be described as not deterministic. The services often don't require full determinism. And also we want to be able to transmit and receive normal data packets on the same network. So the packet bus offers the ability to transmit spacewire packets interleaved with these other services. This asynchronous bus offers priority. I'll speak a bit more about some of these services. So schedule, here's an example with each of the different buses in use. Each time slot, there's a bus. It's possible that not all these slots are used for a particular target initiator. Sorry. Each initiator has a copy of the schedule. Each target has no knowledge of the schedule. They're just a basic RMAP target. They respond when the initiator speaks to them. That means there's no additional logic required in a Spacewire-D target. It is simply an RMAP target. For FDIR, we can check when the transmissions are completed. We use RMAP with acknowledgements, so we know when the packet should come back, when we should get a response. If we don't get a response, then we know there's an error. We can notify the network manager and decide whether we want to continue or not. So with the combination of RMAP, the time codes indicating the start and end of the slots, and the schedule, we can detect faults quite easily. So that's a summary of Spacewire-D. It provides deterministic data delivery using RMAP over existing Spacewire networks. There's no change required to the target devices, and the initiators can be implemented in software. So we foresee that this can be done with no hardware changes. This is all software and existing hardware. It means that Spacewire can be used for time-critical avionics applications and concurrently with payload data handling. There's no need for 2 separate networks. The draft specification is currently under review. The University of Dundee has an ESA contract to develop the draft standard. That was based on requirements from a number of industrial partners within Europe. And also as part of that contract, the University of Dundee, in partnership with Star Dundee, is developing a demo system to show off how this protocol can work and identify any of the problems. In the system, we have multiple initiators using the Castor processor. We have multiple targets, hardware targets. We have RMAP targets in hardware and Castor, and also software targets using Castor again, and also the RTC. The objective is to test all types of virtual bus. And also, Dave Gibson is exploring scheduling algorithms. He's currently doing a PhD, and that's one of the main focuses of his PhD is in some of the scheduling algorithms that can be used on board. So, to get to Dave G's work, he's been implementing Spacewire-D on RTEMS using the Castor BSP that we developed. There's an API, you open, load, and close a bus, setting the initiator, target, and system parameters. There's a bus controller which executes the transactions. We've got structures for the virtual bus, an initiator driver, and a Spacewire router driver. This is an overview. Basically, you wait for a timecode to be received, indicating that it's a new time slot. check within the schedule what's to be executed next, and then execute an open bus or prepare an asynchronous bus queue. I'll speak a bit more about this in a bit, but we treat asynchronous traffic slightly differently. And then the operations are given to the RMAP driver to be dispatched or to the asynchronous bus queue, which is treated slightly differently. So there are services for opening, loading, and closing. There's also helper functions. You can configure the initiator, target, and system parameters and build the data structures. It's important to be able to configure some of these system parameters because they affect how Spacewire-D will function. I'll speak about this in a second. To open a bus, there's 3 parameters. You need a slot or a list of slots, so it's possible that transactions can go over multiple slots. So you can have a slot size, which means you can perform large transactions. This is useful if you're just sending packet data. You can send a large image, for example, within a number of slots. And then you specify a list of targets that the bus is allowed to speak to. This is useful for error detection. So if you have a transaction that's speaking to a target which it doesn't have permission to, that's another way of detecting an initiator, is misbehaving. To remain deterministic, it's necessary for no blocking to be introduced within the routers. So the paths between the initiator and the targets cannot conflict with one another and with other initiator-target pairs. This is the thrust of Dave G's research at the moment, and it's still ongoing, so we don't have a definitive answer to this at the moment. But to give you an example, we have 3 initiators here, 5 targets and 3 routers in the middle. I'm not sure if this is an ideal spacecraft network, but it demonstrates the concepts. It's possible there could be blocking on these routers, but if we have this one initiator speaking to 3 targets and another initiator speaking to 2 targets and none of their paths cross, there's no reason why these 2 initiators can't make use of the same time slot. It's not necessary for an initiator to have full control over the network. So to loading the different bus types differs. For a static bus, you can give it a group of transactions, and whether it's a single shot or a repeating mode transaction group. Repeating means that you can repeatedly perform the same action again and again within a time slot. This can be useful for status information. For example, you can repeatedly request status within a particular time slot. The dynamic bus allows you to load 2 transaction groups, a current group and a next group. This means there's double buffering. So there's always the next group ready to go. And that's how we ensure it's always kept busy. The asynchronous bus is loaded with single RMAP transactions, and these are loaded into a priority queue. This is a bit different from the other 2 types. Before, as I mentioned earlier, it's treated differently in that the time slot preceding the asynchronous bus's time slot, we actually sort out what we're going to transmit in this next time slot. There's a description here, but it's easier just to show an example. We've got 1 millisecond in which we can transmit. We've got all these transactions queued up to be sent, and they all take different times to complete. Within that 1 millisecond, we go through in order. These are ordered by priority, and we work out which ones we can do within the 1 millisecond based on the order in which they're in the queue. So we can do the 600 millisecond one, but we can't manage the 500 one. So we look at further down, and we're able to get these next 4 into the next slot. The next one, this one here, will get done. Oh, excuse me. Yeah. Sorry about that. This next one, the one, I think I've broke the laptop. Yeah, I'm reading fast enough as it is. This is a real test. Yeah, so the second one in the list will get put in the next time slot when it becomes top of the queue. So this is a way of doing priority. It's implemented as a min heap for anyone who knows about binary heaps. Higher priority transactions will get moved out of the queue and placed in back in the next slot. Ordering's based on priority and the insertion time, so it's the order in which they're inserted. And as I said, preparation takes place in the preceding slot to ensure that it's ready when the timecode's received. Closing a virtual bus when it's no longer required, it's closed, which frees any scheduled slots associated with the bus. This is the demo system that we have running. So we have Spacewire-D running on each of these devices. There's a caster. I'm not going to touch this keypad thing just in case. Caster CPCI on the left and in the middle there. We've also got it running on a PCI Express board. On the right is a link analyzer Mark II, which we use to test the timing, so we can see what rate things are going over the link. And on the far right is a brick Mark II that we use to connect to the SDE, and then use that to debug over Spacewire. So there were a couple of problems encountered when we were implementing this. The initiator response time was very important, so being able to respond to getting the timecode and then transmitting the transaction is very important. Initially, we used events to notify a dispatcher task when a timecode arrived. And then we had a nice clean interface to speak to the RMAP driver, which used ioctls and open-close mechanisms. But it was very slow. So we removed the syscalls, removed the open ioctl close, and rather than use events, the first block of transactions after the timecode is actually started off from the ISR. You can argue whether or not that's a great idea, but it certainly reduced the initiator response time. It dropped down from 380 microseconds to 25. So that was the time from the first RMAP command after the timecode reduced to 25 microseconds. The time from a command being fully received until the reply being sent, this was all handled in caster in the RMAP target, is approximately 2 microseconds. So it's very quick. The initiator post-processing time, so that's the time from a reply being received and the next transaction being sent, is around 7 microseconds. So we think we're pretty quick here. This is running at 40 megahertz, as I said. The final chip will run at 200, so I think we'll be pretty good. So that's a very quick whistle-stop tour. The caster chips we expect to be available from Atmel next year. The SDE support's pretty much there. It just needs the user manual updated and a few bits polished off. We've got basic RTEMS support for the chip, and we'll add additional drivers in future. The Spacewire-D draft specification is currently under review. It was presented to the Spacewire Working Group last week. So we're soliciting feedback if anyone has any comments. I think it's available from the Spacewire Working Group website if anyone's interested. And the implementation of Spacewire-D and demonstration system is ongoing, and Dave G in particular is very busy on that at the moment. Thank you for listening.
Okay, questions? Yes.
So there are 3 engines in your design, and you made an assumption about no, poor contention. How good is that? assumption?
How good is the assumption about contention?
Right.
Well, they are completely independent in hardware, so there should be no contention. If I go back to the only contention is on the Spacewire links and in the router. So, for example, if Spacewire engine 2 and 3 were both transmitting on the same link, then you would encounter contention. But the whole point of Spacewire-D is that you design your schedules, so there is no contention on the network.
And you mentioned something about queue extraction. You have
Yeah.
a deterministic, non-deterministic. Do you apply the same method to all different buses?
The queue was purely for the asynchronous bus.
Okay.
For the other two, it's individual transactions, and it's up to the software level to take care of what transactions go into each time slot. So
Okay.
that's handled at the higher layer.
Right. Thank you.
Other questions? Oh, okay, thank you.
Thank you.
Okay, our next speaker is Kenneth P.